right, so, any questions? Any questions on PA2? Are people done with PA2? Okay. So I set a personal record last night while I was working on your PA3. So I've got an include file called wow.h, and I've got a C file called wow.c. And if I take out the comments, this is 10 lines of C code. And when I compile it, I get like tons of errors. And they're weird errors. And it's 1,500 lines of errors from compiling a 10-line C program. That's the best I've ever done. And it actually took me a long time to find my problem. I kind of thought I was losing it for a while. And you know, I always tell people, well, look at the first message, and the first message didn't help me at all, because it's like, I don't even know what that means. Storage class specified for parameter size underscore t. So it you know, I get an error and I want to fix it really quickly first, and then I realize I can't fix it quickly, and then I get like concerned that something weird is happening or I've been hacked or something. And so eventually I figured it out, and it was really clever. So I included my own .h file first, and I don't know why I did that. I just felt like doing something different, and I had a problem in my wow.h, and it was basically corrupting the code in standard io.h, which messed up the code in standard lib.h, and so on and so forth. And in wow.h, all I did, I forgot my semicolon right here. But number sign include really just grabs code from a file and says, and the rest of the file looks like this. So my function definition was followed by the first line of standard io.h, which now made no sense because it had this stuff in front of it. And since that first line didn't work, it caused a whole bunch of things in standard io.h to not work, and then in standard lib and so on. So it's one of those things where, you know, one semicolon costs you 1,500 lines of error from the compiler. So that's a personal record. All right, questions about the GDB quiz in particular? That's coming up due in a few days. And I can talk about it, but I really want you to get in there and start trying to do it, and then ask questions, and we can talk about those particular questions, because I can talk about GDB all day, but that's not necessarily going to help you with your GDB work. And did everybody do quiz 2, which is like due tomorrow? That's just a multiple choice, but it's on basic like C declarations and stuff. GDB quiz, we already went through some of this in detail, so let me just suggest that, remember you can print ampersand a variable to see what its address is. You can print star pointer to see what it's pointing to. You can use the X command to examine memory directly. And inside, this is inside GDB, the print command is fairly powerful. You can print things like size of and put in a name of a type of variable, and it'll tell you how many bytes that thing takes. You can print malloc, and it will call malloc and it will give you a return value from it. You can do all kinds of things inside GDB. It's really kind of like a personal playground. like an interactive version of C where you can run stuff, commands without having to compile them. And it's useful just for that, if nothing else. And the punchline of these last few questions is that if you look at the structure and you figure out how many bytes are required for each of these using size of, the total amount of bytes you need to store one of these structures is less than the amount of bytes that are being allocated. If you look in the array and you see where these things are stored in memory, you see big empty spaces between them. And so there's spaces that aren't being used. And so question 10 is asking you what the address of the first unused byte is in element 0 of the data array. So using the memory map that you've constructed up here, perhaps, and what you know about the size of these different fields. All right, no questions? I'm going to switch gears then. So let's talk about a different kind of data structure called a hash. So hashes are a way to store information. That's what a lot of these data structures are. A way to store information, and a list, we can store information, we can store numbers, we could store words, things like that. Hashes are good for storing information where we want that information to be associated with something else. And so hashes are built around the idea of pairs of information, which we can think of as a key and a value. And I'll give you an example of a key value pair. Might be a name and an office location. And so I want to store the following information, right? Nick is in SBG 115. I think that's my office. And Izad, anyone know what Izad's office is? I'm just going to guess 109, but don't quote me. And Keith might be in AA4 200.
He's Denver?
Yeah, he's not here, but I wanted someone in a different building, and the only building I can think of is AA4. And so on, right? So we could make a linked list of these things, and each node of the linked list could have the person's name and their building and their office number. And then if we wanted to add to that list, that's pretty easy. We just insert it, or maybe we alphabetize by name or something. But searching this list can get expensive. If I've got 1 million entries in a linked list and I want to know, is Nick in one of these nodes, the only thing I can do is just start the Sentinel, follow the links from node to node, and at each node check to see if this is equal to the thing I'm looking for. And that's an expensive operation. And it gets more expensive the more data you have. And it grows by what we call order n. If I double the amount of data, it's generally going to take me twice as long to search for something. And we'll do better when we get to trees. We'll knock this time down significantly, but for just a straight linked list or an array, basically the amount of time is proportional to the amount of data. Unless you get lucky and the name you're looking for happens to be in the very beginning of your structure. If you're unlucky and it's at the very end, right, that balances that out. So the idea of a hash is to be able to do better than that. A hash is a structure that we could actually go in and we could say, tell me if you have any data associated to the key Nick. and the structure will come back and say, yes, I have a piece of data, which is SBG 115. Or I could go in and say, is there a piece of data associated with the name Phil, and it will come back and say, I don't have anything associated with that. And in theory, doing this on a hash is order 1. No matter how much information you have stored, it can retrieve that piece of information in a fixed amount of time, in theory. And that's a whole lot better than order n. Because theoretically, a billion nodes in there, and it still only takes one operation to retrieve any piece of data or tell me that it's not in there. So they're kind of magical. And in practice, they don't work quite as well as theory, but they're pretty close under the right circumstances. Okay, so hashes, first of all, we've got pairs of information being stored. Secondly, we've got extremely efficient retrieval time, and actually really efficient storage time as well. And we can delete and so on and so forth. The other thing to think about hashes, and this is something we've touched on in 224, is that we can think of this as a different kind of array. We could think of this as some kind of array. I'll call it, info. Where we index, instead of with integers, with strings, with names. And if we try to index with a string that's not stored in there, we get back a null or an empty string or something that indicates to us that this is not associated with a value in our hash anywhere. And so this is what we call an associative array. And we talked about associative arrays a little bit with bash. We talked about them a little bit with awk. This idea of making an array that you can index with something other than an integer. And we can index with strings, we can index with binary information, we can index with C programs, we can index with executable images or JPEGs or anything else that we want. Right? It's a completely arbitrary key. And with each key, we associate a value. And this is a powerful way to code information. And it's an efficient way to retrieve information. So if you wanted an online directory that you can put in somebody's name and see their office, right, you could store this information in a hash, and then when somebody types in someone's name, you look in the hash and either find their office information or say that person isn't in the system. And hashes are used a lot. They're used in databases. They're used as part of larger structures. And so PA3 is going to deal with hashes. And we're actually going to make a hash of license plates and associate them with people's names. And I've already generated a random database of license plates and names. And it's got 1,000 of those. So PA3, which we'll go through in detail tomorrow, you're going to write a program that basically ingests a database comprised of license plate, first name, last name, stores all of that information in a hash, and then lets somebody type in a license plate and it will retrieve the name associated with that or tell you that plate's not in the database. And it'll do it really efficiently.
Will we write our own hash function for that?
I'm going to give you a hash function, and yeah, you're going to have to write it or implement it.
Which kind of hash function?
It's going to be basically a weighted sum of the characters in the license plate. So how does this work? I mean, this is magic, right? Order 1. How does this work? Basically, hashes are built on top of arrays. Just a plain old array, which I'll just call my hash table. And let's just say it's an array of 10 entries. And clearly this won't work if I'm going to try to store 1,000 names, but scale it up in your mind. Let's imagine we're just storing a few names in this 10-element hash table. If you just take a name and you store it in the first location, the next name gets stored in the second, and the next one in the third, right? That's just a plain old unordered array, and the search time is order n, right? If I want to find a name, I just have to keep searching. So we do something different. We use what's called a hash function. And what the hash function does is it takes a key and it gives us back an integer. In this case, an integer between 0 and 9. So it's a function that ingests a key, which for us is a name, and gives us back an integer between 0 and 9. And so suppose when we hash Nick, we get the value 7. Okay, then what I'm going to do is right here in location 7, I'm going to store Nick's office. And let's suppose h of Keith is equal to 2. Then down here in location 2 of the hash table, I'm going to store Keith's office. And you're probably already thinking, what if Keith's office also gave you a 7? Okay, we'll get to that in a little bit. But just imagine that there's this function which we can give it a name, that's what our keys are, and it gives us back an integer between 0 and 9, which corresponds to an entry in this array between 0 and 9. And if Keith hashes to a 2, we store Keith's office information in location 2 of this array. And if Izad hashes to a 0, then we store Izad's office information in location 0. Okay, ignoring the details of that, this gives us a really efficient way to retrieve information. If I want to know what Nick's office is, all I've got to do is run it through this function, get a 7, there's Nick's office information. I don't have to do any searching. I just go straight to that spot. Where's Izad's office? Run it through the hash function, it gives me a 0. There's Izad's office information. That's the whole ideal setup of a hash. So it's this associative array. Associated with each of these keys is a piece of information. And the mapping between the keys and where the information is stored, that's what a hash function is. So these hash functions can get very mysterious, but we can do a simple one. So here's an example hash function. It's going to return an integer. It's going to take in a character array. Bless you. We could take the first character of the key. That's the ASCII code of the first letter of the name. That's a number between 0 and 127. We could divide it by 10 and look at the remainder. So that gives us a number between 0 and 9. And we could just return that. So if I use that and I tried to compute the hash function of Nick, letter N is ASCII code, whatever that is. It's 64 plus 14. So So 79 divided by 10, the remainder is 9, so hash of Nick would actually be 9, and I store Nick's office down here. But they can be more sophisticated. If I was trying to hash courses, say I wanted to have a course number and I wanted that to be associated with when it was being offered, what quarter, right? So my keys would be CSE 215, Engineering 270, English 235, right? And the data associated with them would be something like, you know, fall 2020, winter 2020, and so on. And if I use this hash function on course numbers, it's not a very good function because CSE 222, CSE 215, CSE 101 all have the same first letter. And my hash function is going to hash that to the ASCII code of letter C. That's 67 modulo 10. They're all going to try to get stored in location 7. So I could use a better function like the sum from I equals 0 to the length of my key of key bracket I, and take all of that and reduce it modulo 10. So add up the ASCII codes of all the letters in your key and then divide by 10 and take the remainder. Well, CSE 222 is now going to have a different hash potentially from CSE 215, right? Because two of my characters have different ASCII codes. And there's a whole science to deciding on what a good hash function is. And it depends partially on what kind of data is that you're trying to hash. So if you're trying to hash old student IDs from Clark and you wanted to just take the first 3 digits and get a number between 0 and 999, that's a horrible hash because almost everybody's going to hash to 940. But if you did the last 3 digits, you might get a better scattering of where the hash function takes a key. Social security numbers would have the same problem. Hopefully you're not hashing social security numbers. You know, the middle digits of your social security number are based on where you were born, and the first 3 digits are based on when you were born. And so the last 4 digits are effectively random, so you could hash on those, but the other stuff, you'd get this clumping up of multiple keys mapping to the same place. So that's something called clustering. And clustering happens when you have too many collisions. And a collision occurs when 2 keys, let's call them K1 and K2, map to the same value. So 2 keys map to the same value, it means they want to have their associated data stored in the same spot in the hash. And you can't do that, right? This box in the hash table will hold one set of office information. And so you need a way to deal with these collisions, and there's a few different ways to do this. So one approach to dealing with collisions is probing. And the idea of probing is your hash function takes 2 inputs. It takes the key that you're trying to store, but it also takes something called a probe. This is just an integer, starting from 0, typically. And the hash function is some combination of the key and the probe. So maybe it's you know, the sum of each character multiplied by the square of the probe. So if my probe is 0, I get one thing. If it's 1, I get something else. If it's 3, I get something else. And so when you have a key and you want to try to store the associated data in your hash, first you hash it with a probe of 0, and it says stored in location 7. If something is already stored there, you rehash your key, but this time you hash with a probe of 1. And the hash function should give you a different spot in which to store your data. And if that happens to be occupied also, you rehash with a probe of 2. And you just keep rehashing until either you find an open spot or you conclude there's no space left in the hash table. If there's no space left, the table's full and you're kind of done.
Don't you normally use a dynamic implementation if that happens, where you double the size of
Yeah,
the
so
table?
yeah, we'll talk about load factors and growing it. But that's exactly right.
Because for probing, the load factor is more sensitive, right? You like
Yeah.
your max load factor is 0.7 or something ideally versus 0.1.
Right. So probing is one approach, and I usually teach probing and have people do probing in their assignments, and nobody seems to enjoy it. So we're going to work on a different approach, which is called chaining. And in chaining, we have our hash table. And it's an array. But instead of storing the information we want associated with a key directly in the hash table, what the hash table is a table of sentinel nodes. It's a table of sentinels pointing to linked lists. And initially, each of these sentinel nodes points to null, so it corresponds to an empty linked list. If we hash the word Nick, and let's just suppose that's 7, then what I do is I add the associated data, SBG 115, to a linked list whose sentinel node is stored right here. So if this is an empty list, what I'll do is I'll create a new node. I'll store the data, SBG 115. I'll store null down here, and I'll point to that. And when I hash Keith, and that comes out to index 2, this list is empty, so I'll make a node for Keith. I'll store the name of his office, which was AA4200. I don't think that room exists. And I'll put null down here, and there's a pointer to that. Okay, and now when I hash somebody new, and that comes out to 7, I'll come down here. I'm just going to add a new node for Carol into this linked list. And I'm not going to bother sorting this because there's not a whole lot of advantage to that. I'm just going to insert in the beginning because it's really fast to insert in the beginning of a list. Right? Just have the sentinel point to your new node points to the old first node, and you don't have to travel down the list. So I'm going to make a new node for Carol. Anybody know Carol's office? Gotcha. All right, we'll just put her in 105. And I'll have the sentinel point there, and I'll have this point to what was the first node. All right, do you have a question? Okay. So now I'm making these linked lists associated with each location in the hash table. And when I want to find Carol's office number, right, or Nick's office number, I'm going to hash it. I'm going to get a 7. I have the sentinel node of a linked list. Now I just do a linear search down that linked list. All right, just like we've done in PA1 and PA2. Just check each node. If it matches the name, we're done. But to do this, I need to store another piece of information in each of these nodes. I need to store the name associated with it. So my linked list gets a little more complicated.
Would chaining ever use trees instead of linked lists?
You could,
Or
and it would give you more efficient search, right? Because this is about the most inefficient structure we could search, is a linked list. And trees are linked lists with extra stuff added, so we can search really quickly. So yeah, we could put a tree down there. We could put a hash table on there too. So there's this notion of a load factor. And a load factor basically tells you how full your hash table is. There's different ways to compute it. But to see how full your hash table is, right, you could look at how many entries in here are occupied. And that gives you one measure of fullness, right? If 90% of the locations in our array are pointing to something other than an empty list, we can guess that the chance of a collision is probably pretty high. But not all collisions are created equal. If all of our lists only have one node in them, collisions aren't going to be really expensive. So we might want to look at, the average length of the lists in our hash table. And if on average most of them are, one or two nodes, chances are, even when we have a collision, we're going to have to do one or two operations to find our data or say it's not in there. That's not too expensive. But there might be one or two entries where we have a list that's, 1,000 nodes long, maybe because we hashed student IDs based on the first 3 digits, and 940 has this big long list there, right? So you might want to look at maximum length. So there's different metrics you can use, but the goal is to figure out basically how well is this table performing. And if it looks like it's going to be performing pretty well, you just keep running with it. But as you keep putting more and more information in, the performance will degrade. Okay, it's going to get slower and slower to retrieve information. Storing is still fast because we're just storing in the beginning of this case. But retrieval gets slower and slower. So as your table fills up, you may reach a point where you say, my hash table is just too small. I wish it were bigger. And so you can expand it. And you can't just make a bigger array, right? Because our hash function was only working because we were, doing things modulo 10, which gave us a number from 0 to 9. Now if we make our hash table go from 0 to 29, our hash function is never going to use those last 20 entries. We need a new hash function. But if we have a new hash function, then when I go to look for Keith, Keith may no longer hash to location 2. He might hash to location 17. So one way to expand your hash table is to basically go through and rehash everything. Make a bigger table, new hash function, and then go through and take each piece of information in here and just store it in your new table. Now that's an expensive operation, but you can kind of do it in the background while other people are using the old table. And then when you're ready to switch over, you just kind of like go to the new table. And it's kind of a one-time cost, right? So you get a little bit of a delay while you're rehashing and growing the table, but then, you're back to running more efficiently because your table is only 20% full or 10% full or whatever. And there's different approaches to doing all of that as well. All right, questions up to here.
What would be the pros and cons of roaming versus chaining for real application? They both exist because they both have.
They both exist, yeah, which is always an interesting thing to explore. So implementation-wise, chaining is a lot easier, I think. We'll find out. Chaining is a lot easier because it's just an array of linked lists, right? Probing gets complex, for example, when you delete a piece of
Like
data.
dummy knows it, or-
Yeah, if you delete, you can get a gap in your chain of where you have to look for, so you have to keep track of that, so it's more housekeeping. But I don't know beyond that. I think it probably depends on the nature of the data and how the clustering is going to tend to look. Also with probing, ignoring performance, eventually your table will fill up, right? If I have 10 spots in my hash table, all I can ever store is 10 pieces of information. If I have 1,000 entries in my array, I can store 1,000 pieces of information. The performance might be terrible, right? I might have tons of collisions, but I can store 1,000 pieces, but not 1,001. I have to grow the table. With chaining, even if I only have 10 entries in my hash table, I can store an unlimited amount of information because my linked list can grow without bounds. You sacrifice performance, of course, but you're not forced to grow the table. So if you might temporarily need a lot more space, chaining will get you there without having to do an expensive expansion. And if it's just a temporary influx of data and then you're going to delete a bunch of it, right, this might be more efficient to run. Deletion from here is also very straightforward because we know how to delete from a linked list. Deletion with chaining, with probing, you have to keep track that something was there. So yeah, and once you're no longer a computer science student, you're probably rarely going to think about any of this because you'll use a hash package or a hash class, key map, or something like that in Java, and these decisions have been made for you.
So it will make the decision versus chain versus probing for you, or do you have to make that
I mean,
decision?
depending on what package you're using, right? Somebody's already decided how this implementation works, what the hash function is, when it grows based on load factor, all that kind of stuff. And you can tweak some of that,
Yeah.
but you know, mostly from the consumer side, we'll end up not really worrying about it. But from where we are right now, our goal is going to be to actually implement these things in C from a low level up. So we get to play with all these details. So, well, let me talk about the probing example, since it came up. Pick on our 10-element hash table. And let's suppose hash of key comma probe equals first character of key plus the probe modulo 10. This is sometimes called linear probing. And the idea is when we try to store something in our table, if the location where we want to store it is occupied, we'll try to store it in the next location. Right? When we rehash with a probe of 1, we'll take the place we put it before plus 1. And if that's occupied, we'll use a probe of 2. That'll just try the next location after that. So if we want to store the letter A, or apple, right, that's going to hash to location 5, so this is where apple goes. And if we're going to store cat, that's going to go right here, because letter C is ASCII code 67. And then when we try to store ant, right, we're going to hash ant with a probe of 0. That's going to give us a 5. Collision, We'll rehash with a probe of 1. That's a 6. That's open, so we'll store ant right there. Now if I search for ant, I'm going to hash it to a 5. I'm going to check here, and I don't find ant. But that doesn't mean that ant's not in the table. I'm going to rehash with a probe of 1, get a 6, check location 6. There's ant. On the other hand, search for dog. I'm going to hash dog with a probe of 0. And that's going to give me an 8. I'm going to come to location 8. I don't find dog there. I know that dog is not anywhere else in the table. Why? Because this spot is empty. And the only reason that dog would be somewhere else in the table was if I had tried to store dog earlier at location 8 and 8 had already been occupied. Then I would have rehashed with a probe of 1 and I would have tried location 9. But this gets complicated with deletions. So if I delete apple, well, so apple hashes to a 5. I check 5. There's where apple is stored, so I'm going to remove that. Well, I can draw a line through it on paper, but what do I do in the computer? I need to somehow remove this. I need to mark it so that it's not considered to be part of the table anymore. So we have a key, and we have a field called maybe valid. And every time we store something in the table, we'll set the valid bit to be a 1. And then when I delete, I can just change the valid bit to be a 0. The problem with that is if I search for ant, I hash it to a 5, I look here, I don't find ant, and my valid flag says, and nothing is stored here. I might conclude ant's not in the table, because if it was, I would have had a collision here. Well, in fact, I did have a collision. When I tried to store ant, this was not empty. So I need another flag, something like deleted. And when I delete something, I need to set that flag. And now when I'm searching for a key, hash it with a probe of 0, check that location. If you find it, you're done, you found it. If you don't find it and this is occupied with something valid, rehash. If this is not occupied with something valid, but it used to have something, which means the deleted flag was 1, then rehash with another probe.
Does that hurt your space efficiency quite a bit to have 2 separate, I guess it'd be 2 bytes extra for...
You could do 1 byte and just have a flag, right? So use 1 bit in the byte for valid and another bit for deleted. Yeah.
And then also, how long do you have to keep that deleted bit for?
Forever.
Okay.
Yeah.
Because I feel like then you just hit a point where maybe you check them and they're all 1s, and then you switch to checking to see if they're 0s.
Well, yeah, maybe that could speed things up. If I store something else that starts with an A, I'll hash it to a location 5. I'll see that that's not in use. Even though it's got a deleted bit set, I can go ahead and store it in location 5. And I can clear this deleted bit and I can set valid to 1. And if things get really jumbled up at some point, right, you can always rebuild a new hash table. And I just like expanding. But these will get cleared out as we reuse these cells. So it's really just some extra housekeeping to know that if you're looking for something that maps here, you may have to keep looking, even though this doesn't have anything valid in it right now. So deletion and search, have to be aware of that. In search, you just find a spot that's not in use. And there's a whole science to how big your hash table should be and what your hash function should be. Usually these hash tables have a length that's a prime number because these modulo functions work really well with prime numbers, especially when you're probing. And if you've done 215, you remember greatest common divisor, that's where it all comes from. Euclid's algorithm. Your best bet is if your hash table length is not divisible by any of these probe numbers that you might try. All right, so so that's a preamble for PA3. PA3, like I said, we're going to hash license plates with names. So I'll finish writing that up later on today. I'll post it tonight probably, and then we'll talk about it tomorrow and look at how we might implement this. All right, I will see you tomorrow then.